This is Lab 5, the world's largest rope swing. The video used in this lab is of a person jumping off a natural bridge in Utah and swinging on the world's largest rope swing. The purpose of this lab was to predict the motion of the jumper and relate it to the motion of a pendulum. It was also to determine the speed of the jumper and determine the tension in an ideal rope and of a real rope. It was also to create a computational model using VPython that will predict the motion of the system using Newton's second law and the energy principle. The initial conditions used in this lab were that the mass of the person was 70 kilograms, the weight force was 9.8 meters per second squared, the rope length was roughly 46 meters, the drop length was roughly 40 meters, the length of rope from the ground was roughly 3 meters, and the angle at the bottom of the swing was 90 degrees. These are the initial conditions that were put into the VPython program. Using the energy principle, we are able to find the velocity at 90 degrees. We find that delta E equals W plus Q and that Q equals 0. Therefore, delta E equals W. We let our system include the jumper and the rope so that there are no interactions in the surroundings and delta E equals 0. Delta K equals 1/2 the mass times the velocity of the final squared minus 1/2 times the mass times the velocity initial squared. Delta U equals mass times gravity times delta H. Ki plus Ui equals Kf plus Uf, and in this case Uf equals 0 and Ki equals 0. Therefore Ui equals Kf, and we are left with mgh equals 1/2 mv final squared, and this gives us a final value of the final velocity to be roughly 28 meters per second. These are the formulas for kinetic energy, potential energy for gravity, and potential energy for the spring that were put into the program. This is how we calculated the tension at 90 degrees. The bottom of the rope swing will have the greatest tension and the greatest velocity. F net is equal to the force of the perpendicular force plus the parallel force. F parallel at the bottom equals 0, so F net is only equal to F perpendicular. Therefore, we are able to solve F perpendicular and F net to be mass times the absolute value of the change in velocity squared divided by the radius, which gives us 1191.78 newtons. F net is also equal to the force of tension plus the force of gravity. The force of gravity is equal to negative mg. Therefore, we manipulate the variable and find the force of tension to be 1877.8 newtons. This is the formula for the momentum principle that were put into VPython. This is similar to finding the velocity at 90 degrees, except that the Ki equals 0, whereas Ui equals mgh, initial in this case. Therefore, we get U plus mg h initial equals 1/2 the mass times the final velocity squared plus mg h final. Therefore, we manipulate the variables to find that the final velocity at 30 degrees is 34.5 meters per second. The tension at 30 degrees is found by finding that the jumper avoids the ground by 3.05 meters. So h at 30 degrees is equal to the original h plus 3.05 meters. Again, F parallel at the bottom equals 0, so F net equals F perpendicular. In this case, we find that the force of gravity is equal to mg cosine 30. Therefore, we find that the force of tension equals 1513 newtons. The stretch in this experiment was found by treating the rope like a spring so that we can use the ideal spring force. We found this for the 90 degrees and the 30 degrees. The formula used was the force of tension equals Ks times S, and S for each of these individual cases was 0.065 meters and 0.052 meters respectively. In conclusion, velocity and tension are both greatest at 90 degrees. Acting as a pendulum, the speed going down will be greatest at 90 degrees, and as it passes 90 degrees, it will change direction and slow down. The tension of a pendulum will be greatest when it is hanging down It must overcome the gravitational force to continue to swing. Thank you for watching my video.